Hi, I always say DC hurts much less than AC. For example, I have my rectifier circuit here that generates close to 170 volt DC output from the 120 volt AC input. It can even turn on a lamp. But if I touch the output, I can barely feel it. While if I touch the 120 volt AC input, it'll hurt me to the moon and beyond. Well, I haven't touched that in a while. Maybe it doesn't hurt anymore. No, that's stupid. The reason is that body has capacitive properties that allows more current to run through the body for AC, and so it hurts much more. But how much is that capacitance? Let's measure it. To measure capacitance, we need to measure impedance, which like resistors is simply equal to the effective voltage divided by effective current. Everyone has access to the AC voltage, which is the 120 volt AC city power line. To measure the current through my body, I connect my current meter to the AC line and hold the probe on one side and only touch one of the AC lines. Well, that was a pretty bad idea. I couldn't keep steady enough to read the meter. And I could have... See, the thing is that the current meter is like a short circuit and it's not gonna isolate your body against high voltage. Well, rather than checking my own body capacitance, let's start with a real capacitor. At least real capacitors can't get electrocuted. Well, using 120 volt AC is a pretty bad idea. Don't mess with AC power. You can measure the capacitance using something like this RLC meter. The problem is that these things are very easy to use. Also, they measure the capacitance only at a certain frequency, like 1 kHz, while I want to know the human body capacitance at different frequencies, like 50 or 60 Hz of the city power. The reason is that all capacitors change value based on frequency. A good way to measure capacitance at any frequency is to use a function generator and a series resistor connected to it. Here I have my function generator, which is outputting a sine wave, and I have a series resistor on its output, which I am probing both sides of it, as you can see on the scope. If you ever wonder what's a sine wave, well, this is a sine wave. With nothing connected to the output of the resistor, the input and output waveforms look exactly the same. If my body only has resistance, then when I touch the output, only the amplitude of the signal drops, like when I touch the output with a resistor, like this. But when I touch the output with my fingers, you can see that the output waveform shifts forward, and this is an indication that my body has some capacitance that's delaying the output waveform. Here I've zoomed in on the edges of the signals. Now all I need to do is to measure the amount of shift in time and plug it into this formula. And voila, I have the human body capacitance for a specific frequency. Here is the measurement for a range of frequency. So my body capacitance at 60 Hz is around 5 nanofarads, which combined to my body resistance almost doubles the effective current that runs through my body compared to the same DC voltage level. And that is why I previously measured that you have to double the DC voltage to hurt the same as AC. No! According to my sensors, the AC hurts at RMS levels half of the DC level. Everything comes together now.